We're going to go ahead and look at simplifying roots. When you're simplifying roots, you want to make sure that you have no fractions left inside of a root, that you have no roots in the denominator of a fraction, and that anything you can take out of a root has been taken out. So we're still going to go ahead and use a lot of the same techniques that we did in our last section. We're dealing with a square root, so we're going to try to rewrite the inside as something squared. So 25 is 5 squared. A to the fourth is an a squared times an a squared. B to the ninth is a b squared, a second b squared, a third b squared, and a fourth b squared. Well, that would only be b to the eighth. So that means we're going to have another b hanging around. Now, your square root will end up canceling out anything that has a squared on it, and so that square root will cancel out the squared, leaving us with a 5, this a and that a. Then we're going to have each one of these purple b's pulled out in front, and then this maroonish b to the first does not have a squared on it, so your square root doesn't do anything to it, so it stays inside of your root. And now all we're going to do is simplify what's in front to a 5a squared b to the fourth, still with that b inside of your root. So that's the main difference in some of these problems today compared to yesterday's, is that not all the roots will disappear. So here, if we do this one, we'd rewrite our 16 as a 4 squared. Our y to the fourth is an xxx. And then, did I say 3x's? Just an x squared and an x squared. And then our y to the 11th is a y to the squared, y squared, y squared, y squared, and y squared, which would be a y to the 10th. Still need one more y hanging around to get up to y to the 11th. Now, anything that has a perfect square on it inside of a square root will come out of your root, so you'll have a 4, an x, and an x, and then all your green y squareds come out just as normal y's, and we can't do anything to this purple y to the first because it's not squared. It's going to still stay hanging out inside of your root. And so then we just simplify what's in front with a 4 x squared, y to the fifth, still with our y inside of our root. So that's how we're going to be simplifying a lot of these roots. Now we're going to get to problems of what happens when you have a fraction inside of a root. Well, first of all, you're going to start off by applying your root to the top and applying the root to the bottom. Now, you could leave it as just a 9 to the first, but if you can, rewrite any number inside of a root as a number to a power. That's always going to be helpful. Now, this 3 squared on the bottom does not help us a whole lot because we have a cube root. If it was a 3 cubed on the bottom, well, then we could simplify it and pull it out. But because your exponent here does not match what's in front of your index of 3, that doesn't simplify or cross out. So what we need to do is we need to multiply by a special form of 1 so that we end up getting perfect cubes on the bottom like this. We had a 3 inside of our root. We had an x inside of our root. We want to try to get the exponents on that 3 and that x to be matching what's in front of our index of 3. Because then we could go ahead and simplify that down to just this on the bottom. That's what we want to try to get to, is this. So you got to think yourself, okay, cube root of what times the cube root of what would give me that? Well, a 3 squared times just another 3 would give me a 3 cubed. And also an x times an x squared would give me an x cubed. So I'm going to multiply the bottom by the cube root of a 3x squared, and if I multiply the bottom by that, I could also multiply the top by that, because I can only multiply by special forms of 1. So multiplying out the bottom, we do get this, and then that bottom, your cube root would cancel out all your cubing, leaving you only with a 3x. We still now have to multiply the top. It's a cube root times a cube root, so you can multiply it as one big root. And then you just multiply what's inside, 2 times your 3x squared, which would be a 6x squared. So we simplified the bottom here. Top we're going to leave as this. Then you'd want to see, could we do anything to simplify the top? Well, the exponent on our x is 2, which is smaller than our index of 3 in front, so we cannot simplify our x squared. And the only thing that gives us a 6 is a 2 and a 3. Neither one of them are perfect cubes, so we cannot pull anything out of the top. So that's it. That's our final answer. So in this problem over here, you apply the root to the top and the root to the bottom like we did here. At this point, you have two options. You could either try to get the root out of the bottom by multiplying by a special form of 1, or you could go ahead and simplify each root. I like the idea of simplifying each root because you can actually deal with smaller things in the long run. We're dealing with square roots, and you know that an x cubed is really an x squared times another x. Or we have a y to the 7th, and we're dealing with a square root, so we're going to try to write things as something squared. So that's a y squared, a y squared, a y squared, with another y hanging around. Now, anything that's something squared inside of a square root, we know we can pull out. So this x squared on top, we can pull out in front, and it becomes a normal x. Here our y squared, and our y squared, we can pull out in front of our square root because our square root undoes each one of those y squareds and makes them just a normal y. So we'd have a y in front, which is a y cubed. Can't do anything with that y to the first inside of my square root, so that stays there. We know we're not done because we still have a squared in the bottom, or a square root in the bottom. So you got to think, okay, what do I need to multiply it by so that inside of my square root, by the way, this y cubed is here because we had a y cubed in front. We want to try to get to the square root of a y squared because we had a square root, so we need to end up with a square root. We want our exponent on our variable to match our index. There's no index written here. It's assumed to be 2, so we want to try to get a y to the second, or a y squared, to show up in the bottom. So you got to think y times what is a y squared, and that would be the square root of y. And if I multiply the bottom by that, I got to multiply the top by that. So now I can multiply out the top, multiply what's in front of my roots, which is just an x, multiply what's in my roots together, which is an xy, and I would have this. So now I'm going to still have the top, still have that y cubed, and then you got to think, oh, the square root of a y squared, well, that's just another normal y. So on the bottom, I have a y to the first times a y cubed, so I end up with a y to the fourth. There's nothing I can do to the top because I have a square root, which is an index of 2 in front, even though it's not written, and these exponents on my x and y are both 1, which are smaller. So on this problem, we'd want to go ahead and apply the root to the top and the bottom. And then you'd want to get the root out of the bottom. Once again, we have a cube root, so we want to try to get to the cube root of each thing on the inside raised to the third power. Because we know if we get to this, where our exponents match our index in front, that our root's going to cancel out our powers, just leaving us with that 3a. So you need to think 3 times what is a 3 cubed? Well, that's a 3 squared. And you should realize that an a times an a squared is an a cubed. So that's what we're going to multiply the bottom by. And if we multiply the bottom by that, we got to multiply the top by that because that's a special form of 1. And multiplying by 1 does not change the value, only the appearance. So on the bottom, we've already gone through and simplified all that. So now we just have to multiply the top. A cube root times a cube root, so you just write it as a cube root and multiply what's inside. We have a 2 times a 9, and then we have our a squared. Now, the only thing that gives us 18 is a 2 and a 3 squared, which we had here. Neither one of them are perfect cubes, so we know that that 18 is not going to simplify. And the exponent on our a is smaller than our index in front, so we know that that's not going to simplify. Now, as a side note down below here, we can add and subtract roots if the number in the root is the same. Because here you'd have 3 of the root 5s plus 7 more of the root 5s gives you a total of 10 of those root 5s. So it's just like taking a 3x plus a 7x, you get a 10x. That root 5 here is kind of like that label. Just like a 3 feet plus a 7 feet would be a 10 feet. So 3 of the root 5s plus 7 of the root 5s is 10 of the root 5s. So when you're multiplying roots, it's really multiplying, because we have everything being multiplication here. It's multiplication between our root in the number. It's multiplication in between our parentheses. Everything's multiplication, and remember, you can multiply in any order you want. So you can multiply what's inside, in front of your roots, your 3 and your 4, multiply what's inside of your roots, and it would simplify down to this. So that's how you multiply roots. And you saw some of that on a couple of earlier problems. So here we need to simplify. You want to look at the factors of 45 that are perfect squares. That's a 9 and a 5. Factors of 80 that are perfect squares, that would be a 16 and a 5. Factors of 20 that are perfect squares, that is a 4 and a 5. We know we could not necessarily just add and subtract these together to begin with because the roots are different. So we're going to just simplify each root. Now here, we're still going to have this 3 in front. And then the square root of that 9 is also a 3. Then we'd have the square root of that 5 just hanging around. Here we're going to have our 5 left in front. The square root of our 16, which would be a 4 in front, then that square root of 5 is just going to hang around. Here our 4 is going to stay in front. Then we'd have the square root of this 4, which is a 2 in front. And then we'd still have that root 5 hanging around. So here we really have a 9 of the root 5s. Here we really have minus 20 of the root 5s. Here we have plus 8 of the root 5s. Now that all these roots are the same, we can just add and subtract these together. 9 of the root 5s minus 20 of the root 5s plus 8 of the root 5s is a total of negative 3 of those root 5s. Here we have 2 terms times 2 terms, just like we were doing with normal algebra, like an x plus 5 times an x minus 8, and multiplying those out, foiling. We want to do the same thing here. So you multiply your first terms together. 2 times 3 is a 6 in front with a root 3. Multiply your outer terms together. The root 9 comes from multiplying what's inside of this root times what's inside of this root. The negative 2 comes from the 2 times the negative 1 here. Multiply the inside, the green, 3 times 3 root 3, which would be a total of 9 of those root 3s. Multiplying your last terms together would be positive times a negative, so we know it's negative. A 3 root 3 times another root 3 would be a 3 root, and multiply what's inside your roots together, and you get 9. Bring this down. Now know that root 9 is a 3, so it's 2 times 3. Bring this down. 3 times the root 9, which is another 3. So now we can go ahead and simplify this a little bit. 9 of the root 3s is being added to 6 of our root 3s is a total of 15 of the root 3s, and this is just a 6. This is a 9 over here, so we can take negative 6 and subtract 9, and we will get this. So here we're multiplying our roots together in between. So we're going to multiply what's in front, 2 times 3, then multiply what's inside of our cube root. So it's going to be cube root, and we get a 64a cubed. So we're going to have this. Cube root of 64 is a nice, neat number of 4. Cube root of our a cubed, the index in front cancels out the exponent of 3 here, so we just get 24a. So you should be able to do the last few problems on your own, and then just watch the video to make sure that you get them correct. So here we're going to simplify your root. Go ahead and think of root 75 as a 5 times 3, or 25 times 3. that 25 comes out as a square root of 25, which is a 5. That root 3 doesn't change it, so we get 15 of the root 3's. Looking at the next term, 48 is a 16 times 3. We like the 16 times 3 because 16 is a perfect square. So we're going to get a 2 with a 4 in front from that square root of 16, still with our root 3 hanging around, which gives us a total, and when we look at what's in front, a negative 8 with root 3. Then the last term is just a root 3 just hanging around. Now all these roots are the same, so they could be combined together. We have 15 of the root 3's minus 8 of the root 3's plus really only 1 of the root 3's gives us 8 of the root 3's. Last slide here, we FOIL, we multiply the first terms together. 2 times 5 is 10 of those root 5's. Outer terms, 2 root 5 times 7, root 7 would be a negative 2 in front. Multiply what's inside your roots together, the 5 and 7, that's where the 35 comes from. You do your inner terms. 5's not in the root, the 4's not in the root, so you multiply those two together, bring down your root 6. Multiply the last terms. Multiply what's in front. 4 times minus 1 is minus 4. Multiply what's inside your roots together. You get 42. And this is it, because root 5 doesn't simplify. Root 35 doesn't simplify because it's only a 5 times 7. Neither one of them are perfect squares. 6 doesn't simplify inside of our root because that's only 2 times 3. Neither one are perfect squares. And 42, when you look at the prime factorization, is a 2 times 3 times 7. Neither one of them are perfect squares, so we have no like terms. This is all we can do. Now, notice on this last one here, you have 2 terms in the bottom. Remember, terms are things added or subtracted together. If you have a root over one of them but not the other, then you want to multiply by what's referred to as the conjugate. Same exact thing that's on the bottom, except you switch the sign that's in between the 2 terms. It was negative, so we're going to switch it to positive. If I multiply the bottom by that, I'd have to multiply the top by that. So now all I'd have to do is FOIL the bottom, multiply my first terms, my outer terms, 2 times root 6, my inner terms, a negative 2 root 6. My last terms, a positive times a negative is a negative, or root 6 times a root 6 would be the square root of 6 squared. You'll notice my inner and outer terms here drop, so I just have a 4, and then this would just be a minus 6 here at the end. On the top, all I'd have to do is take 3 and distribute it through here. 3 times 2 is 6, 3 times my root, and I just have to bring that down. So now, bring that down on top, simplify the bottom down to a negative 2. Some people might choose to leave it here. Typically, we don't like to leave a negative in the bottom. Now, remember, it's not a negative exponent. A negative exponent would go to the other part of the fraction, but we don't have a negative exponent, so don't confuse it with that. I'm going to just take the negative from the bottom and put it on the top, because you should know that 3 over negative 2 is the exact same thing as a negative 3 over a 2. So basically, I'm going to take the negative from the bottom, move it up to the top, and distribute it through. And when I do that, I end up just getting this.